We have Otar Sepper giving our grad talk. He did his undergraduate at NYU, and now he works with Professor Andre Lebed. And today he will be talking to us about the Schrodinger equation and how it can arise in classical mechanics.
Yes, thank you. So the style of this talk is basically more for entertainment rather than to expose an active research area. But this is something I took up recently. So the basic question I want to ask is, can classical Hamiltonian mechanics reproduce quantum mechanics without relying on external postulates? And the important word here is reproduce. It doesn't mean derive, or it doesn't mean predict quantum mechanics, but simply reproduce conventional non-relativistic quantum mechanics without relying on any concepts outside of classical mechanics, such as, for example, the correspondence principle or the Ehrenfest's theorem. So let's review those postulates briefly. So Ehrenfest's theorem relates the time rate of change of expectation values and puts them in a form that is similar to Newton's second law of motion, F equals ma, but not quite, because we have expectation value outside of this derivative here. And if you want to really associate it with Newton's second law, you would have to assume that we can put the expectation values inside here, which can work if the wave function is highly localized, right? We know how to reproduce classical mechanics from quantum mechanics. So one of the assumptions here is that the potential varies on a scale much less than the de Broglie wavelength. Okay? So actually, this works well for quadratic potentials. If you take a harmonic oscillator, you can find the fact that the average value of x squared is exactly equal to the average value of x quantity squared, but not for higher powers. So that's a problem. So we can easily go from quantum mechanics to classical mechanics and then use the correspondence principle. And by the way, this derivation already assumes the Schrodinger equation, because how we get it? We basically say that the expectation value of an observable is the integral of the square of a wave function times the operator, and then differentiate it with respect to time, and then substitute the d psi dt, which comes from the Schrodinger equation. So this definitely relies on some kind of intuitive or an external postulate, which is not present in classical mechanics. Now, so correspondence principle works well. However, Dirac gave us a prescription which says that the commutator of two quantum mechanical observables can be, in a way, mapped from a classical mechanical quantities, functions of phase space coordinates, by taking the classical Poisson bracket and then multiplying it by complex unit I. And of course, there are limitations and ambiguities in the traditional mapping from classical to quantum pictures, because first of all, there is no unique way to assign an operator to a classical function of phase space variables, simply because P and Q don't commute. So then we resort to these weird symmetrizing rules of adding xp plus px and dividing by 2, and all those textbook examples, right? Also, spin degree of freedom is absent in this kind of mapping, because spin is not a function of phase space variables. So there is no straightforward generalization of spin from classical mechanics to quantum mechanics. And also another important point is that there is no analog of anti-commutator in classical mechanics. I mean, I have the Poisson bracket, which is fine, but anti-commutator is important in quantum mechanics because when we fix its value, we determine the symmetry of the wave function. That's how we get fermions versus boson statistics, right? It's unclear what anti-commutator would even be in classical mechanics. So the goal of this talk will be to just reproduce conventional quantum mechanics from classical Hamiltonian mechanics without using any of these postulates. So here we go. So first, we'll consider kind of a motivational example. We'll consider dynamics of a classical phase space, which is parametrized by just two coordinates, P and Q, and under a particular Hamiltonian. Okay? So the phase space looks like this. We have variables P and Q, which are functions of time, and Hamilton's equations, dynamical equations of motion, determine this trajectory from some initial time to final time t prime. Okay, so no problem there. I mean, these are just time derivatives of Q and P equals partial derivatives of the function h, and the function h is just any arbitrary function on the phase space, right? So Q and P in Hamiltonian mechanics are called the canonically conjugate variables, right? We know this from textbooks, and actually we have to treat them on an equal basis. It's not necessary to associate position necessarily and momentum or velocity with them. We know that from the theory of canonical transformations, P and Q can actually be complicated functions of real position and momentum as long as their Poisson bracket is preserved, right? Then they're canonically conjugate variables. And they can be even interchanged in certain cases. So we can think about these as phase space coordinates. And for the moment, forget about physical picture of momentum and position for now. Okay? So we have a phase space coordinate represented by an ordered pair, QP. And let us introduce an operator, I, whose action on this phase space point, ordered pair, is defined as follows. So I, acting on this pair, switches the variables and then reverses the sign of the second one. Okay? No problem, I can always just invent this kind of an operator. So it's an operator that simply acts on phase space ordered pair. Next step is to take the time derivative of this equation, and note that differentiation will commute with this operator. I mean, it's easy to check. First you switch, and then you differentiate. That's the same as you differentiate first and then switch them, okay? So we get I times d by dt of this quantity, qp, equals d by dt of this, of course. And then I use Hamilton's dynamical equations to relate dp dt to partial h, partial q, with a negative sign is important here, right? And time derivative of q is partial h, partial p. But that, by definition, is just the phase space gradient of the function h. Remember, function h is an arbitrary function on this phase space variables. In multiple dimensions, you can replace here q1, q2, q3, and so on. But essentially, this is just the gradient of the Hamiltonian function on the phase space. So we get this equation, operator I times d by dt of the phase space point qp equals gradient of h. So this is our first important result. And then next, we note that the action of this operator on the phase space point qp corresponds to a rotation by 90 degrees in complex space, because what it does, it switches the q and p variables and then negates the second one. So this is just, if we parameterize the point qp as q plus ip in complex space, then the action of this operator I corresponds to simply multiplying this ordered pair by a complex number I. Let's check. So I times q plus I squared, which is minus 1 times p, which is exactly what the operator I does to the pair qp. Right? So we can identify qp with a single coordinate, a complex coordinate psi, which equals q plus ip, and then the equation that we got on the previous page becomes I d by dt of psi equals the phase space gradient h. So I want to say right now here that I have done nothing external to classical mechanics, and this is just another way to rewrite Hamilton's equations dH dq equals p dot, dH dp equals q dot, and so on. The entire classical mechanics is contained in this equation. There's really nothing else. Angular momentum and all of those things are still functions on phase space variables. So pretty much we can say this is just a compact way to rewrite classical mechanics using this psi, which is just a complex coordinate qp. So what's next now? This is very general, right? H can be anything. So let us now take a particular example, and we pick a Hamiltonian.
I have a question.
Yes.
So you said there are no conditions on H, but if you have psi as an independent variable on the left hand side, then the H has to be a function of psi, which means H has to be an analytic function.
Yeah. All those assumptions.
Just as you.
Yes, the same assumptions that go into Hamiltonian mechanics are preserved here. Of course, we also need to supply initial conditions to solve this, right? So now the trajectory looks like this. This now is a same phase space, but parametrized by a complex function psi at initial time t, and then it propagates to some final time t prime. So this is basically Hamilton's equations of motion. And if you give me initial conditions, I can solve this, and we're pretty much done. Okay? So now we'll take a
But psi is restricted to be q plus ip.
Yes.
That's all. It's not a general function. It is q plus ip.
It's exactly. It's just q plus ip.
Okay.
Right. It's a coordinate which parameterizes phase space in terms of this ordered pair. This ordered pair is just the dynamical variables of the Hamilton's equations, basically.
I have a
So-
question.
yeah.
So you have the operator I, which actually reverses the direction of p, the
Sorry?
conjugate momentum. The operator I,
Mhm.
the capital I, it reverses the direction of momentum, the conjugate momentum, right? So do you think
It's,
that
yes, so it switches the variables around.
yes.
It makes p into q and q into p, and reverses the sign of p. Because in the Hamilton's, there's a hint side here, and you will see in the Hamilton's equations, the minus sign is important when partial h, partial q, right, gives us, it's like the negative gradient of the potential, which gives us the force, right, dp dt by Newton's second law.
The particular reason why I was asking this because do you think there's a relation between a time reversal operator
Well, in time reversal operator in quantum mechanics simply replaces t with negative t. But in quantum mechanics, we also need to make complex conjugation, which doesn't really work here because then you have q minus ip, and then when you switch it, there will be two minus signs. Right? Yeah, but you have a valid point. I mean, there's really nothing here that is extra to this original prescription given by Hamilton. Okay, so now let's take a particular Hamiltonian. This is just a symmetric form of a classical one-dimensional harmonic oscillator. E will be an arbitrary constant. So let's apply this formalism. It's easy to take the gradient. Taking the derivative with respect to q just gives us eq. With respect to p gives us ep. So we plug this into this equation. So I d psi dt is eq comma ep. But since e is a constant, arbitrary constant, we can pull it out. And we have e times our ordered pair, qp, which is by definition psi. So what we have reproduced here is a map of the time evolution of a classical phase space point onto a stationary state solution of a Schrodinger equation with which we can identify E as the energy. Okay? So this is just a mathematical mapping.
But psi is still q plus ip.
Psi is still q plus I. I have not identified psi with any kind of wave function or any quantity outside of classical mechanics. Right? So far it's just mathematics. Any questions? And of course I took a particular Hamiltonian here to reproduce this. But now I want to...
Is this a Hamiltonian dependent? If we took a different Hamiltonian, you would reproduce this? No?
Yes, of course we know that we can add to the Hamiltonian a total differential, right? A total time derivative which does not change the equations of motion. So Hamiltonians and Lagrangians are in general not unique. So probably you could add something to here, do a variational calculation, and arrive at the same equation. But at least we know that this particular classical system does map onto the stationary state Schrodinger equation. But I want to see.
That's not the case. It maps onto this function
Right, this function.
only.
Only this function, right. But I haven't associated this function with any quantum mechanical variables yet. It's just a mathematical analogy at this point. So now what I want to do is ask if we can generalize this formalism to reproduce the complete Schrodinger equation with an arbitrary potential psi. So to do this, we need to introduce a function of space and time corresponding each to Q and P. So we're going to go from a finite dimensional classical mechanics to infinite dimensional classical mechanics. Essentially, you can imagine a string, and the first coordinate here, let's say, gives us the amplitude of vibration at a given position in time, and the second coordinate, let's say, gives us the momentum or velocity of that piece of the string. So we're talking about classical field theory. And x here is, the x can be thought as just fixed positions in space. They are independent of time. Or they can be thought about as, let's say, fixed points on a lattice, or something like this. So now we have infinite dimensional classical mechanics described by classical field theory. And these fields now themselves become the dynamical coordinates. But that's not something strange because, like we know, for example, in the classical electromagnetism, the vector potential and its derivatives can become the dynamical coordinates in the Lagrangian. And by doing variational calculations with respect to those coordinates, we can derive Maxwell's equations, for example. So our previous example with the Q and P evolving, right? It will just correspond to a fixed value of x, just one single point. So this will be maybe a zero-dimensional classical field theory. Okay? But we want to take this general form, and now from textbooks on classical field theory, we know that the Hamiltonian becomes a density, and again, its actual form is not unique because we can add total derivatives to it. The equations of motion are not going to change. So if you look up the canonical, quote-unquote now, canonical equations for the Hamiltonian density, they say that the time derivative of this generalized momentum, I guess, is given by the partial derivative with respect to coordinate, and then the space derivative, the gradient, with respect to the derivatives of the same coordinate, right? So we identify now the conjugate momentum coordinate to the field to be this pi, which is the gradient of phi.
Can I just ask, just for the sake of understanding the notation, is it important that you switch from using Q to represent the coordinate to X when you move from just the canonical coordinates to fields?
The X that I'm using now is just a parameter that fields depend on. It's not a coordinate in a sense, it doesn't depend on anything. It's just space. X you can think about as a lattice. These are points fixed in space. And then at each value of X, we can evaluate the numerical values of the fields, essentially.
So these aren't fields as a function of position in physics?
No, fields are a function of position and time. Right? Because look, so phi sub I right here are functions of position and time. But this is different now. This is not the same position and time as Q and P in the classical phase space. Because those were the canonically conjugate Q and P. These are actual positions in time. You can think about X as the length of the string, time as an independent parameter, and phi to be a quantity dependent on let's say, an amplitude of vibration. So
Another question.
Yeah.
Right, so in classical field theory, you would associate the pi as the time derivative of the phi. So why isn't x over here? Why would you?
So Sorry? What is what?
So why is it not a time derivative of the field operator phi instead?
The time derivative is equal to this. This equation can be derived from a variational calculation by integrating the Hamiltonian density, varying psi to psi plus delta psi, and this will be the generalization of like the Euler-Lagrange equations.
Right, but in that case, I mean, I'm just saying that you identify the conjugate momentum as a gradient of the phi instead of the time derivative.
Instead of the time derivative, exactly. The gradient instead of the time derivative.
That's not normal, though, isn't it? That we're just, I think, is that the confusion? And that normally it's P is Q dot, dQ dt?
P is Q dot, but in this case, remember how the electromagnetic Lagrangian works. There is a vector potential A, and the magnetic field is curl A, which are derivatives of A. So to derive Maxwell's equations, we vary this integral with respect to A itself and with respect to derivatives of A. There is no time derivative involved there. It's in Jackson. But this is more general. This is just from classical field theory.
I have another question. So you said that your phi's, you mapped Q and P into phi sub i's?
No, I didn't necessarily map it. The previous example was a finite dimensional classical system. Now I'm in a different world, but by analogy, I had two dynamical phase space variables, Q and P, and I'm taking two fields, phi 1 and phi 2. And I can associate them only intuitively with canonically conjugate momentum and position concepts. But we can think about these phi's as just two functions of space and time.
But do the relationships still hold Q plus IP is all you're calculating?
You will
The
see that, yes.
effectiveness of
Yes,
Q.
we will get, yeah, we will get that. So, next step will be to construct a Hamiltonian which will be analogous and motivated by our one-dimensional example. Okay? So it will be quadratic in all the coordinates. The momenta, similar to kinetic energy, and the phi's. But you see, this term is not that surprising because in textbooks on quantum field theory, we often see a representation of an operator V in a second quantized form like this. We see this expression often, second quantization. So it's psi squared times V. Psi squared are the fields. So in the classical field theory, this will be just a natural generalization. But we don't even have to say that. I can always pick any Hamiltonian I want, essentially, because, and then do a variational calculation and see what happens. But this Hamiltonian does have meaning here because it introduces a density, right, which is quadratic in all the coordinates. So it's similar to the harmonic oscillator example that I introduced in the finite dimensional case. So because these canonically conjugate momenta are partial derivatives, all I have to do is just plug them in, and I get this Hamiltonian density. And the next step is to apply these, I don't know what you call them, I guess Hamiltonian Lagrange equations, and find that, you see, the partial derivative with respect to phi gives us phi times v, and then partial derivative with respect to the derivative of phi, differentiated again with respect to x, gives us the negative second derivative of phi with respect to x. So far, this is just a substitution of this particular Hamiltonian into the formal, so to say, dynamical equation. So now, motivated by our finite dimensional structure of canonically conjugate coordinates, right? It had dHdP and also minus dHdQ. We make a canonical transformation where the fields, phi 1 and phi 2, are simply the reverse conjugate momenta of each other. We can do that. In the theory of canonical transformations, we can make mapping from a set of variables to another set as long as commutation, not the commutation, the Poisson brackets are preserved. they're valid canonically conjugate variables. You can check that that is the case here. So pi 1 is the conjugate momentum to field phi 2 coordinate, and pi 2 is the reverse conjugate momentum to phi 1. And we have this equation on the previous slide. So we simply plug in phi 2 and phi 1 in their appropriate place. So for example, pi 1 here becomes negative phi 2. And what we get is two equations, coupled equations for the fields phi 1 and phi 2. Okay? So this Hamiltonian, essentially a variation of calculation using this Hamiltonian, or the classical field theory, gave us two dynamical coupled equations for the coordinates phi 1 and phi 2. So now I will do exactly the same thing. I will invent or just associate a single complex coordinate, which is phi 1 plus I phi 2, and calculate its time derivative, and then substitute the coupled equations. Right? There is a factor of I multiplying the first, and you can check that this is just a simple algebraic expression. This operator can be factored out, multiplying again the same complex quantity psi, phi 1 plus phi 2. And what we get is this equation. We get essentially a dynamical equation for the complex now coordinate psi. d psi dt equals negative Laplacian of psi plus v of psi, which means we have taken infinite dimensional classical mechanics, classical field theory, and mathematically reproduced an equation which looks like the Schrodinger equation of quantum mechanics. I did not derive the Schrodinger equation. I did not predict the existence of quantum mechanics, nor did I ever associate psi with any kind of quantum mechanical variable so far, right? Not a density, not a probability amplitude, or anything like this. But at least as far as mathematical formalism is concerned, it does reproduce. Now, can we do a little bit more and actually associate any physical meaning to this, right? So what physical interpretation can be given to enhance this analogy to quantum mechanics? Well, first, we always like to check if the same concept of a probability density works in this mathematical formula. So we'll consider the modulus squared, phi 1 squared plus phi 2 squared. Phi 1 and phi 2 are just real fields, right? So far, we don't have to know the existence of quantum mechanics. We can just think about classical terms here and check which equations are satisfied. So let us introduce a quantity analogous to the current. I will call this a phase space current. So it's a phi 1 times the gradient of phi 2 minus phi 2 times the gradient of phi 1. And it's easy to check if we use these coupled equations for the fields that the continuity equation is satisfied. All I have to do is just take the time derivative of this quantity, the gradient of this quantity, plug them in, and see that the continuity equation indeed is satisfied. So basically, the classical phase space in infinite dimensional systems can be used to reproduce our normal Schrodinger equation without even knowing the existence of quantum mechanics. Now, what about the Poisson brackets? Well, you can check that if we take psi and its complex conjugate, right, and simply use chain rule, because there's a phi 1 plus I phi 2, when we take the derivatives in the Poisson brackets, a numerical factor of I simply comes out as a multiplication there. So Dirac's prescription is indeed satisfied in this case. So, maybe this is not all a coincidence. So to summarize here, we used purely mathematical groupings of classical variables, used only classical Hamilton's dynamical relations for classical field theory, and did not introduce any concept outside of classical mechanics. A crucial concept was the ordered pair, because we need two fields here. We need psi 1 and psi 2. This formalism cannot be done with just one field. Right? And we have demonstrated that a phase space continuity equation is satisfied, and also that perhaps the structure of classical mechanics is much richer than we think.